You apply a voltage difference to a conductor. The electric field exists in the conductor. Charges move. You get a flow of charge. We call it a current. Now the question is, how much current do you get? That's what we want to know. And the way you know is from Ohm's law. So let me give you sort of a definition of Ohm's law. Well, actually, Ohm's observation that is relevant to materials of interest in 1827. J equals sigma E. So first, let's talk about the commentary here. This is not a law, okay? So you learn as a child that in science we have theories, those are ideas, and we do experiments to test them, and then if they always work, then we promote it to the level of law. Right? That's a nice story, but it's almost the opposite is true for some reason. It seems to never work out that way. Plenty of things are called a law. Ohm's law is called a law. It's not a law. Not a single material exactly obeys Ohm's law. No material. Many materials approximately obey Ohm's law, but it's not really a law. Many things that are laws are still called theories. Relativity theory. If anything is a law, it's relativity. But we often still put theory on there. Have you ever heard anybody say relativity law? No. Evolution, the theory of evolution. Well, there's probably a good reason a lot of people call that theory. Let's not get into that one. But there are a lot of laws and theories where it's completely backwards. Let me give you another. Ohm had two laws. There's also Ohm's acoustic law, which states that a musical sound is perceived by the ear as a set of pure harmonic tones. It is well known to not be quite true. Right? So there you go. Law, theory, forget that thing you were told as a child about theories and laws. So this is not an exact law, but it'll work. It's good enough for what we're going to be doing. And it is then that the amount of current you get in terms of current density is simply proportional to the field that you apply. Now, I know you're used to thinking of V equals IR, and we'll get to that on the next board. But actually the way it was originally stated was not in terms of voltages and currents, but in terms of current density, the current per unit area, and electric fields, not voltages. Of course, we know they're very closely related. Another thing to keep in mind, and then the thing to keep in mind is that sigma is the conductivity of the material of the wire, say, or the material in the wire. Okay? And it's in a unit that we'll talk about more in a minute of inverse ohm meters. So we use omega to talk about resistivity and conductivity in inverse ohm meters. Sigma is not the surface charge density in this case, okay? There are only so many Greek letters, and we reuse them. So first part of the class, sigma meant coulombs per meter squared. It was the surface charge density. Now sigma means the conductivity. And you just have to use context sometimes to know which one we're talking about. Usually when they give you a number and they give you a unit, then you can tell. We try not to have a single problem with both sigmas in it, but I can't make any promises. I've seen it happen in textbooks before. Okay? So anyway, that's Ohm's law. Now let's see if we can put it in a more useful form.